Welcome to the Sleepy Science Facts. It's a gentle moment to find comfort and relax, allowing the sounds around you to fade softly. As you settle in, just take a relaxed breath. If you find joy in these quiet explorations, feel free to like and subscribe whenever you wish, as a soothing way to join our journey through the wonders of science. High above, thousands of airplanes glide effortlessly. Their wings, designed with a careful shape known as an airfoil, play an essential role in that graceful flight. On the top, the wings are curved, while the bottom remains flatter. This special design is not just for looks, it creates differences in air pressure as the air flows over and under the wings. The air moves faster over the curved top, leading to lower pressure, while slower moving air beneath the wing brings higher pressure. This difference creates lift, a gentle upward force that allows the airplane to rise into the sky. This fundamental principle has remained steady, allowing aircraft to manage the forces of flight with remarkable efficiency. Over time, this simple yet effective shape has been the backbone of reliable flying. As you think about those mighty wings, consider how this steady design contributes to the quiet safety of air travel, carrying people smoothly through the sky. The wings continue to be a marvel of physics, quietly guiding us into the night above, ready for further exploration and understanding. A gentle aspect of an aircraft's design is found in its flight envelope. This term refers to the range of speeds and altitudes in which an airplane can operate safely. Within this envelope lies a balance, carefully defined to ensure that the aircraft remains stable and secure during its journey through the air. When the airplane moves within its optimum range, it can respond predictably to the dynamics of flight, avoiding conditions that might lead to stalls or structural failure. The upper limits of this envelope are determined by factors such as engine performance and wing design, while the lower limits ensure that the airplane maintains enough speed for lift. As the aircraft flies higher, the air becomes thinner, leading to shifts in lift and drag. This interplay defines the contours of the flight envelope, guiding the engineering that keeps everything in harmony. Understanding this range allows the wings to perform their role without overextending, creating a safe space where the aircraft can glide smoothly. This careful balance of forces enables stability, guiding the airplane on its tranquil path through the sky, ready to explore further into the calm of the night. The interior materials of an airplane are an important aspect of its overall design. Seats, panels, and various surfaces are crafted from selected materials, chosen for their balance of durability and comfort. Over the years, as the aircraft carries passengers through the skies, these materials undergo a gradual but inevitable process of wear. With each flight, elements like fabric, cushioning, and even the finishes on surfaces experience subtle changes. This slow degradation occurs as textures become smoother and colors may fade. In time, as this wear accumulates, the need for refurbishment arises. This process helps to refresh the interior, ensuring that comfort and safety remain a priority. Replacing worn-out fabrics and updating paneling not only revitalizes appearances, but also maintains structural integrity. Each tender touch strengthens the connection between the aircraft and its environment, ensuring that it continues to provide sanctuary to those aboard. This intricate cycle allows the airplane to adapt and renew itself, quietly standing ready for future journeys as it carries memories and dreams across the endless expanse of sky. Over the years, as airplanes soar through clouds, they experience a continuous cycle of stress with every takeoff and landing. This repetitive action places strain on their metal structure, which, while designed for durability, can still develop what is known as metal fatigue. As the airplane climbs into the sky and then descends to touch the tarmac, the materials that make up its frame endure tiny, almost imperceptible changes. These changes manifest as minute cracks forming within the metal, often hidden from view. Although these cracks may remain small for a long time, they quietly spread under ongoing pressure. This slow progression can eventually lead to significant concerns if not properly monitored. Engineers and technicians work diligently to inspect these structures, ensuring that even the smallest imperfections are detected and addressed. This careful attention helps preserve the integrity of the airplane, allowing it to safely navigate through the vast open sky. The balance of stress and strength plays a crucial role in maintaining the harmony of this intricate system. Each part of the aircraft is in a constant state of observation and care, ready to continue its journey through the air. Over time, technology continues to evolve, bringing about gradual improvements in the design and efficiency of airplanes. Older models, once cutting edge, may begin to feel the weight of their age as newer designs emerge, featuring advancements in fuel consumption and aerodynamic performance. This evolution occurs steadily, often unnoticed, until the differences in efficiency become significant. As these advancements are integrated into new aircraft, the gap widens. Older airplanes, which may have once been considered reliable and effective, may no longer match the performance of their modern counterparts. This change does not happen overnight. Rather, it unfolds gently, revealing a slow shift in the landscape of aviation technology. The ongoing development fosters a quiet sense of progress, which can lead airlines to reconsider the longevity of their older fleet. The decision to retire these older planes often stems from a desire to optimize operations and embrace the enhanced capabilities of the latest models. This cycle of renewal allows the aviation industry to breathe new life into the skies, quietly moving toward enhanced efficiency, even as the older designs gracefully fade from service. In the quiet environment where airplanes await their journeys, a subtle process can begin to unfold. Metal components, essential to the integrity and strength of the aircraft, are susceptible to corrosion over time. This natural phenomenon occurs when moisture, salt, and air combine, leading to gradual deterioration. Initially, this process can be nearly imperceptible, moving silently beneath the surface of the shiny exterior. As years pass without careful maintenance, the effects of corrosion may become more pronounced, slowly eating away at the materials that hold the structure together. Each minute detail of the metal can change, often unnoticed for decades. The quiet progression of corrosion can sometimes raise safety concerns as the resilience of these components diminishes. Regular checks and careful upkeep can help mitigate this slow decay, ensuring that the integrity of the airplane remains strong. The delicate balance of maintenance versus the natural elements invites a sense of care and attentiveness. Beneath the surface, materials continue their quiet struggle against time and environment, allowing the larger structure to stand firm, awaiting its next opportunity to soar. Within the serene space of an airplane cabin, time unfolds in gentle layers, affecting every surface and material. The fabrics that line the seats can begin to show their age, with colors fading softly under the influence of light and the constant presence of many travelers. Each thread weaves a story of countless journeys, yet this journey also leads to a gradual wear, an inevitable fading that does not shout but whispers of the past. Materials, too, can experience this quiet passage. As the cabin doors open and close, the elements contribute to a slow deterioration. The cushions, once plush and welcoming, may lose their buoyancy, while the textures of the walls and ceilings bear the marks of gentle contact over time. This gradual process can create a subtle discomfort that contrasts with the initial allure of a freshly designed interior. With the natural progression of wear, there often comes a moment when the cabin's aesthetics call for attention. The gradual fading and tearing of materials encourage refurbishment, allowing for a loving renewal that honors both the structure and those who travel within it. As the cabin undergoes transformation, it remains a sanctuary of movement, quietly adapting while maintaining its core essence. Through this gentle cycle of aging and renewal, the cabin space continues to embrace the warmth of countless flights, ever ready to welcome new journeys. Within the intricate web of airline alliances, a gentle rhythm unfolds, reflecting the ever-changing dynamics of the market. Over the span of 10 to 15 years, these alliances can rise and fade, shaped by various influences that swirl around them. Each phase gently emerges, driven by the shifting needs and aspirations of the airlines involved. At the forefront, the interconnectedness of airlines creates a tapestry of operations and choices, where collaboration may bring about new efficiencies and shared resources. With time, external factors, such as economic conditions or passenger preferences, can shift this balance. A gradual transformation takes place, sometimes leading to the dissolution of existing partnerships. During these cycles, alliances adapt to their surroundings, perhaps merging or evolving into new configurations that reflect the latest patterns of the aviation landscape. This quiet evolution embodies the resilience of the airline system, reflecting both the challenges and opportunities that emerge over time. Just as roots expand and intertwine below the surface, these alliances navigate their existence, ever in motion, yet firmly rooted in their purpose. The gentle rise and fall weave a story of persistence and change, leaving room for future connections and possibilities to blossom in the tranquil sky above. Jet engines find their most harmonious operation at high altitudes, typically soaring between 30,000 and 39,000 feet. In this serene expanse of the atmosphere, the air thins, creating an environment where fuel combustion occurs with greater ease. The reduced air density allows the engines to harness oxygen more effectively, facilitating the intricate process that powers flight. As the aircraft ascends, the cooler temperatures at these heights contribute to optimal performance, helping to maintain engine efficiency. The design of jet engines takes into account this delicate balance, with components crafted to navigate the unique conditions of high-altitude flight. The interplay between air pressure and temperature becomes a gentle dance, allowing engines to operate with less drag and more thrust. Over time, this careful engineering leads to smoother journeys as the engines work with the altitude to maximize their capabilities. The peaceful skies envelop the aircraft, providing an ideal backdrop for this delicate balance of forces in motion. Each ascent transforms the experience, quietly reinforcing the synergy between altitude and engine performance, with the potential for further exploration lingering softly in the air. Vortex ring state emerges as a rare but significant condition affecting helicopters, and certain fixed-wing aircraft can also encounter this phenomenon under specific circumstances. It involves the aircraft descending into the very air it displaces, generating a swirling motion of air that circles back around. This interaction can create a pocket of turbulence, disrupting the smooth flow of air over the wings or rotor blades. The onset of vortex ring state leads to a sudden and noticeable loss of lift. As the aircraft continues to descend, the delicate balance between lift and weight falters, resulting in a feeling of heaviness and loss of control. This gentle yet disorienting situation arises from the aircraft becoming entrained in its own descending airflow. Understanding the characteristics of this condition contributes to a greater awareness of the complexities in aerodynamics. Vortex ring state serves as a reminder of the intricate dance between air and aircraft, where the movements create conditions that can alter the experience of flight. The phenomena linger softly in the atmosphere, inviting contemplation of the many forces at play above us as thoughts drift quietly into the night. Heat generated from an airplane's engines plays a significant role in its overall structure. As engines operate, they produce warmth that radiates through various materials of the aircraft. This process of thermal expansion occurs as the materials respond to the increased temperatures. Metals, plastics, and composites each expand at different rates, creating subtle shifts in their dimensions. With time, consistent exposure to this heat can lead to a gradual fatigue in the structural components of the airplane. Repeated expansion and contraction may alter the integrity of materials. Over years of service, these changes could result in microfractures or slight distortions, influencing the characteristics of the airplane. Managing this heat becomes essential, allowing engineers to monitor the structure and maintain its performance. The long-term behavior of these materials invites contemplation of their resilience and adaptability in the face of constant change. Each part of the aircraft, responding to the cycles of temperature, embraces the rhythm of flight. In this interplay of heat and materials, a quiet energy weaves through the airplane, contributing to its storied life in the skies. The weight of an airplane significantly affects its performance, particularly during takeoff and landing. Each aircraft is designed to handle specific weight limits, encompassing not only the structure itself, but also fuel and other payloads. When the weight increases, subtle changes occur in the dynamics of flight. Thrust must be greater to lift off the ground, and this requirement can alter the way an airplane is operated. Heavier loads lead to longer distances required for takeoff and landing, influencing various performance characteristics. The wings, crafted with precision, depend on lift generated by air flowing over them. As weight increases, the airflow dynamics shift, necessitating adjustments to speed and angle of attack. Operational procedures may be modified to ensure safety and efficiency, allowing the aircraft to perform optimally within its limits. Over time, engineers closely monitor these changes, continuously studying how an airplane responds to differing weights. This ongoing relationship between weight and performance draws attention to the delicate balance that exists within the structure, ensuring that each flight unfolds with care and precision, ready to carry on through endless skies. The fuselage, forming the central structure of the airplane, plays a crucial role in defining its integrity and overall performance. Often composed of a blend of aluminum alloy and reinforced plastics, this combination carefully balances strength and weight, which is essential for efficient flight. Aluminum, known for its durability and low density, provides the framework that is robust enough to withstand the stresses of high-altitude pressure. Reinforced plastics complement this structure, adding flexibility and resilience while further reducing overall weight. These materials work together to maintain the airplane's shape, even through the fluctuations in pressure experienced during ascent and descent. Over time, this harmonious design allows the fuselage to endure the rigors of flight without compromising safety or performance. As the airplane navigates through changing atmospheric conditions, the fuselage remains a steadfast anchor, bridging the cabin and wings with stability. Each component contributes to an intricate balance that enables the aircraft to soar, ready to explore the vastness of the sky with grace and precision, carrying on in seamless continuity. Over the lifespan of an airplane, its weight can gently increase. This gradual change often occurs as modifications are made or additional equipment is added. Each new component, whether for enhanced technology or upgraded systems, contributes a small weight that can accumulate slowly but steadily. As these adjustments take place, the overall mass of the aircraft may grow, influencing how it performs in the sky. The balance between weight and design remains delicate. Changes can impact the dynamics of flight, leading to variations in fuel consumption and overall efficiency. A heavier airplane may require more thrust to ascend and maintain altitude. The engines calibrated for optimal performance must adapt to this new weight, encouraging careful attention to how each addition influences the aircraft's operation. This ongoing evolution allows for insights into the physical limits of flight, revealing how internal changes resonate through the entire structure. As the airplane continues its journey, the interplay of weight and performance unfolds, highlighting the graceful balance of engineering and natural forces, allowing it to sail through the skies with ease and poise. Advanced composite materials find a significant role in the construction of airplanes, particularly in the wings and tail sections. These materials are crafted from a blend of fibers and resins, designed to be lightweight yet remarkably strong. The use of composites allows for a sleek design, which contributes to the aerodynamic efficiency while maintaining structural integrity. The durability of these materials is noteworthy. They are specially engineered to resist the wear that comes with time and the stresses of flight. As an airplane soars through the skies, it encounters varying forces that could lead to fatigue in less sturdy materials. Composites are built to withstand these challenges, ensuring that the structure remains robust for many years. This resilience contributes to the overall lifespan of the aircraft, creating a system that gracefully supports the journey of each flight. Over time, the materials continue to perform effectively, holding up under changing conditions while maintaining their strength and reliability. In this way, the airplane continues to embody the harmony of science and engineering, moving serenely through the atmosphere, ready for each new adventure. The paint on airplanes serves an important role in their overall composition, offering a protective layer against the elements. However, over time, this paint is subject to the natural forces of sunlight and weather, gradually leading to its degradation. Ultraviolet rays from the sun can make the colors fade slowly, resulting in a softer, less vibrant appearance. Rain, wind, and temperature changes also contribute to this gradual change, exposing the plane's surface to a variety of conditions that can wear down the protective coating. The effects of this weathering are not only visual. The deterioration of the paint can influence the aircraft's corrosion protection. The underlying materials may become vulnerable if the protective paint layer thins or peels. This can prompt the need for maintenance to ensure that the aircraft remains in top condition. Over many years, the delicate balance of nature and the craft reveals itself in this process of gradual change. Even as the paint fades gently, it tells a story of resilience against the open sky. Each airplane may wear its experience, standing as a testament to the years spent in flight and the forces it has encountered. The quiet evolution of the surface speaks of time and the enduring strength within, allowing for future journeys while embodying a serene connection with the atmosphere. With the passage of time, technological advancements continually shape the world of aviation. As new designs and materials are developed, older airplane models naturally fall into a different category, becoming less prominent in the skies. These once innovative aircraft, with their state-of-the-art features, may gradually find themselves overshadowed by newer models that offer greater efficiency and enhanced safety. The evolution of materials, such as lighter yet more durable composites, allows modern planes to achieve better fuel economy and performance. Meanwhile, the integration of advanced systems for navigation and control further enhances the reliability of newer designs. This gradual shift means that the older models, while still functional, may operate with less precision or efficiency compared to their contemporary counterparts. Over the years, the differences can become more pronounced. Features that were once groundbreaking may become standard, leading to a quiet transition where older airplanes no longer meet the innovative benchmarks set by newer designs. Each of these older aircraft holds its own stories and experiences, carrying with them the weight of engineering breakthroughs that have paved the way for the future. As this gentle transformation unfolds, it reflects the cycle of progress and change within the realm of flight. The passage of time brings both a sense of nostalgia and a calm acknowledgement of the advancements that continue to soar through the skies. This story of progression continues, quietly marking the movement towards new horizons. In the tail section of an airplane, the design features control surfaces that play an essential role in the aircraft's stability and maneuverability. These components, often made from lightweight yet durable materials, contribute significantly to the overall structure. Their careful construction ensures that the airplane maintains its essential handling characteristics throughout its lifespan. Crafted to withstand the various stresses imposed during flight, these surfaces are engineered with precision. They can endure the forces of the air flowing over them, providing the necessary adjustments to keep the aircraft on its intended path. The materials used in their construction are chosen not only for their strength, but also for their ability to resist fatigue over time, allowing the control surfaces to function effectively with consistency. This durability translates into stable performance as the aircraft remains responsive to the pilot's inputs. The gentle design of these tail components allows for smooth movements without excessive wear. Such resilience supports the airplane in maintaining equilibrium through countless flights, enhancing the overall experience of soaring above the earth. The harmony of lightweight design and robust construction fosters a sense of reliability. As these systems work together, they contribute to the feeling of effortless grace in the air. Each journey is marked by the careful orchestration of forces, moving as one to glide through the skies. In this quiet continuity, the tail section stands as a testament to engineering that embraces both simplicity and strength, allowing for a seamless connection between the airplane and the atmosphere surrounding it. The engines of airplanes utilize high-strength alloys, carefully selected for their ability to endure the demanding conditions encountered during flight. Within these powerful systems, the materials are capable of withstanding extreme temperatures and pressures generated by combustion and aerodynamic forces. This resilience allows them to maintain their structural integrity even after long periods of operation. Each alloy is engineered to provide strength and stability while remaining lightweight. This balance is crucial as it contributes to the overall efficiency of the aircraft. Over time, these alloys demonstrate remarkable durability, resisting wear and fatigue. The microscopic structure of the materials helps them adapt under the stresses of intense heat, allowing the engine to function smoothly across various phases of flight. The interplay of these high-strength alloys enhances the longevity of the engines, ensuring they perform effectively throughout numerous journeys. Each component is designed to work harmoniously within the overall system, allowing for consistent operation and reliability. As the airplane soars through the skies, the steadfast nature of these materials contributes silently yet significantly. The engines serve as a robust core, enabling flight with a quiet assurance. This delicate balance of strength and durability resonates throughout, providing an essential foundation for the ethereal experience of flying through the vast expanse above. Fatigue and stress over time can lead to subtle deformities in the fuselage of an airplane. As the aircraft experiences repeated cycles of pressure and load, small changes may occur in its structure. These alterations, while often minor, can gradually affect the way the airplane handles during flight. The fuselage, essential for maintaining the integrity of the entire aircraft, is designed with materials that are resilient, yet even these can experience shifts under prolonged stress. The physical properties of the materials enable them to absorb and distribute forces during operation, but repeated stress can result in tiny variations in shape. Over the years, these slight alterations may necessitate reinforcements to ensure the aircraft continues to perform safely and effectively. These structural adjustments can be vital for maintaining balance, stability, and control. Monitoring the fuselage's condition allows for careful management of these changes, ensuring that all elements remain in harmony. This ongoing relationship between material and stress reflects the enduring nature of engineering, where strength and resilience work together over time. With each journey taken, the fuselage continues its silent story, adapting subtly yet steadfast to the ebb and flow of flight. The quiet endurance of these materials illustrates a dynamic balance, inviting further exploration into the mysteries of flight. The energy consumption of airplanes, an essential aspect of flight, is often described in terms of fuel efficiency. This measurement reflects how much fuel is used to transport passengers over a specific distance, typically noted as 3 to 4 liters of fuel for every 100 passenger kilometers traveled. The continuous evolution of technology has led to gradual improvements in the ways airplanes are designed. Aerodynamics plays a crucial role. As the shape of an aircraft becomes more streamlined, it encounters less resistance as it moves through the air. This reduction in drag helps to enhance fuel efficiency, allowing the aircraft to utilize fuel resources more effectively. Advancements in engine technology also contribute to this process. Modern engines are being developed to harness energy in more efficient ways. With each innovation, the balance between energy consumption and performance shifts slightly, leading to a more efficient flight experience. The interconnectedness of design and engineering illustrates how the physical attributes of an airplane influence its energy dynamics. Each improvement builds upon the last, creating a gentle evolution in fuel efficiency that supports the ongoing journey of flight. This serene progression invites curiosity about the future, as each flight continues to carry with it the promise of smoother, more efficient travel. Corrosion, a natural process, quietly impacts the materials within airplanes, especially those composed of metal. Over years of exposure to moisture and salt, which can be prevalent in various environments, these components begin a gentle transformation. The interaction between the metal and these elements leads to a gradual weakening as the surface of the metal changes and deteriorates over time. This subtle deterioration unfolds in layers. At first, the effects may not be immediately visible, but as time passes, the cumulative impact becomes more pronounced. Inspections are essential, serving as a regular checkup to observe the condition of the metallic parts. These thorough assessments allow for the identification of any early signs of corrosion, enabling the maintenance of the airplane's integrity. The natural cycle of corrosion reflects the ongoing relationship between materials and their environment. As parts are monitored and cared for, the airplane, resilient in its design, can continue to navigate the skies. Each inspection offers a chance to ensure that the elements work harmoniously, inviting a sense of calm in the endless dance of nature and engineering. Fuel systems in airplanes naturally endure a gradual accumulation of deposits over many years. This slow, gentle buildup occurs as fuel flows through the various components, interacting with the materials and the environment. Tiny particles may settle and combine with substances in the fuel, leading to the formation of deposits that quietly layer themselves within the system. Over time, this process can begin to influence engine performance. If these deposits are left unattended, they might result in clogging, which can disrupt the smooth flow of fuel essential for optimal functioning. The delicate balance within the fuel system relies on consistency, and with regular maintenance, these issues can be managed effectively. Regular servicing allows for the cleansing of these deposits, ensuring that the passages remain clear and that the system operates as intended. The gradual nature of this accumulation invites an understanding of the dynamic interactions at play as materials respond to their surroundings. In this ongoing relationship, the health of each component contributes to the overall harmony of the airplane, preparing it for its continued journey through the skies. Flap deployment asymmetry arises when one wing's flap extends to a different position than the other during critical moments like landing or takeoff. This interaction between the components of the wing affects the airflow around each side of the aircraft, resulting in a subtle imbalance. Such a condition may lead to one wing generating lift differently than the other, which causes a gentle yet noticeable shift in the aircraft's attitude. As the plane navigates through the air, this imbalance often necessitates quick adjustments. The pilots, attuned to the delicate dynamics of flight, respond to these shifts with precise movements. Their careful control helps restore harmony to the aircraft, ensuring a smooth transition through the skies. The engineered structure of the wings, designed to support various configurations, also plays a role in how these asymmetries are managed. Variations in flap deployment, while potentially concerning, are part of the nuanced balance of flight mechanics. As the systems and forces interact softly, the aircraft continues its steady path, gliding through the atmosphere with an underlying strength, ready to adapt as needed. Fuselage designs are carefully crafted with a focus on minimizing fatigue over time. This thoughtful engineering ensures that the aircraft can handle countless cycles of takeoff and landing, which are among the most demanding phases of flight. The structure of the fuselage, with its smooth lines and reinforced sections, is built to withstand the stresses that arise during these operations. Materials used in the fuselage must be selected for their ability to endure. Lightweight composites and sturdy alloys come together to create a balance of strength and flexibility. As the aircraft ascends and descends, the fuselage experiences varying forces, and the design helps distribute these stresses evenly, preventing weak points from developing over time. The internal framework supports this resilience, with interconnected components that enhance stability. Every element is considered, contributing to the overall durability of the aircraft. This thoughtful approach ensures that through each cycle, the fuselage remains a robust shell, providing both safety and longevity, ready for the next journey ahead. Climatic changes have a subtle yet significant influence on flight routes and fuel efficiency, unfolding gradually over decades. As global temperatures rise and weather patterns shift, the air currents in the atmosphere can change as well. These alterations may affect the routes that aircraft take, as pilots and flight planners seek the most favorable conditions for travel. With warmer temperatures, wind patterns may strengthen or weaken, leading to adjustments in flight paths to avoid turbulence or to maximize efficiency. Such shifts can impact the amount of fuel needed for flights, as aircraft strive to glide smoothly through the air with the least resistance possible. Longer-term trends may emerge, showcasing how these evolving patterns can both challenge and adapt the flying experience. As these changes unfold, the aircraft's design also plays a role in maintaining efficiency. With structures optimized for varying atmospheric conditions, the aircraft continues to adapt to the changing world around it, moving with the gentle push and pull of the air, ready for the flight ahead. The maximum altitude for commercial jet aircraft typically hovers around 45,000 feet. This altitude serves as a delicate balance point, where various factors play a crucial role in the aircraft's operation. Above this height, the atmosphere shifts in ways that demand careful consideration. The thinner air reduces the availability of oxygen, which poses challenges for human physiology. Cabin pressurization becomes vital, ensuring that passengers and crew can breathe comfortably throughout the flight. At such heights, the design of the aircraft must account for these changes, maintaining a safe and stable environment within the cabin. Structures and materials are carefully chosen to withstand the external pressure while providing a controlled atmosphere inside. As altitude increases, temperatures can drop significantly, further influencing the performance of the aircraft and the comfort of those aboard. The harmony between altitude and human well-being remains a key focus in aerospace design, ensuring that the journey remains serene, even as the aircraft glides through the upper reaches of the sky. Airplanes are designed with weather-resistant systems that allow them to function effectively in a variety of environmental conditions. The surfaces of these aircraft are treated with special coatings, which help shield them from rain, ice, and intense sunlight. These materials work to minimize the accumulation of moisture, preventing any potential issues that could arise from harsh weather. As planes ascend through clouds, they encounter varying temperatures and pressures. Within these systems, management of ice formation is crucial. De-icing mechanisms are integrated into wings and tail surfaces, ensuring that any ice that forms is efficiently removed. This helps to maintain the smooth flow of air around the airplane, which is vital for stability and efficiency during flight. Components such as engines and electronics are also enclosed within protective casings that resist both moisture and temperature fluctuations. This attention to detail ensures that all systems continue to operate optimally, even amidst relentless winds and shifting weather patterns. The combination of robust materials and clever engineering allows the aircraft to glide through harsh environments, remaining resilient and steady. The interplay of these elements contributes to the overall reliability essential for a safe journey through the skies. Airplanes can sometimes create a phenomenon known as wake turbulence. This occurs when an aircraft moves through the air, displacing the surrounding atmosphere and leaving behind rotating air currents. These invisible spirals, generated primarily from the wingtips, linger in the sky for some time after the larger plane has passed. As they drift through the air, they can be influenced by wind patterns, creating a changeable landscape of turbulence. For smaller aircraft following closely behind, these air currents can present challenges. The strength of wake turbulence is influenced by several factors, including the size and weight of the aircraft that created it. The larger the airplane, the more significant the turbulence it leaves behind. and when a smaller plane enters this disturbed air, it may experience unexpected rolls or shifts in altitude, as the turbulence can disrupt its smooth flight path. This interplay of forces in the atmosphere allows wake turbulence to extend far beyond its source. Pilots are trained to be aware of these conditions and take them into account. The careful design and engineering of airplanes help them maintain stability even in turbulent air, allowing pilots to navigate through these challenges with skill and assurance. The dance of air currents continues, shaping the experience of flight, creating a delicate balance in the vast expanse of the sky. Runway and airport expansion tends to follow a natural cycle, closely linked to the growth of populations and the rising demand for air travel. This relationship evolves over time, approximately every 10 to 15 years, as more people desire to connect with distant places. Each cycle reflects the interaction between the ever-expanding networks of communities and their desire for smoother, more efficient travel pathways. As more travelers take to the skies, airports begin to feel the pressure of increased activity. The air traffic patterns shift and the number of flights naturally increases. Over time, this escalation calls for additional runways and facilities to accommodate the surge in passenger numbers. With careful planning, airport designs evolve, allowing for the expansion of physical structures while maintaining a flow of operations. As the cycle continues, planners assess existing infrastructures and identify areas that may benefit from enhancement. Runways may be lengthened or reinforced to support larger aircraft. Terminal buildings might expand to create more space for travelers and amenities. This slow dance of growth aligns with the natural progression of a city's population, illustrating how the environment adapts to changing needs and desires. The rhythmic ebb and flow of these cycles foster a continuous transformation, shaping the landscape of air travel in gentle, steady waves. Airplanes exist in a delicate balance, where gravity constantly pulls them toward the Earth, creating a force that must be meticulously countered for flight. This gravitational pull is a powerful aspect of the natural world, acting upon every object, including these intricate machines. The wings of an airplane are designed with precision to harness the principles of aerodynamics to produce lift. When an airplane moves forward, air flows over the wings, which are shaped to create differences in air pressure above and below them. The design of the wing generates this vital lift, allowing the airplane to rise and sustain its altitude against the constant force of gravity. As the engines propel the aircraft forward, this interaction between air and wing shapes results in lift, a force strong enough to overcome the pull of gravity for a steady ascent. The harmony of these forces enables airplanes to soar gracefully through the skies, making it possible to traverse great distances. This ongoing interplay of forces continues, while adjustments in speed, angle, and wing configuration maintain the balance necessary for flight. As the airplane glides through the air, it remains a testament to the elegant and precise relationships found in nature. Ice can accumulate on the wings of an airplane, especially when flying through clouds or in conditions of high humidity. This buildup occurs when moisture in the air freezes upon contact with the cold surface of the wing. Over time, the ice can grow in size, changing the shape of the wing and altering the airflow around it. This alteration can influence the lift that the wings generate and may affect the overall stability of the aircraft during its journey through the sky. Eventually, the ice reaches a point where it can no longer adhere to the wing, causing it to shed suddenly. This event, known as ice shedding, is often unexpected and can lead to abrupt shifts in the balance of forces acting on the plane. A sudden change in lift can lead to temporary variations in altitude and stability. Wings are designed to manage these changes, allowing the aircraft to regain control as the ice breaks away. The careful engineering of wings and control surfaces helps to ensure that even in these moments, the airplane can respond and adjust to maintain a steady flight path. The dynamic nature of the environment around an airplane underscores the intricate balance of forces at play, continually contributing to the experience of flight. As these processes unfold, they represent another aspect of how airplanes interact with the atmosphere, always in a state of movement and adjustment. In certain situations, aircraft may experience control reversal, a phenomenon where the expected response from the control surfaces becomes unpredictable. This means that when a pilot makes a movement, such as pulling back on the control stick, the airplane may react in an unexpected way. Instead of ascending, it might descend, or instead of turning left, it could veer right. Such counterintuitive responses can arise from a variety of aerodynamic factors. Changes in airflow over the wings and control surfaces can disrupt the intended motion. Design flaws in the aircraft's structure may also contribute, leading to a misalignment in how the aircraft responds to commands. The intricacies of aerodynamics create a delicate balance that sustains flight. Control reversal highlights the complexities of this balance as different forces interact continuously during flight. Despite the confusion this may cause, aircraft are constructed with multiple system redundancies to stabilize their behavior. This allows for adjustments to be made, helping restore predictability amid changing conditions. In this way, the aircraft remains engaged with its environment, adapting to the ever-shifting nature of flight. The ongoing dance of aerodynamics serves as a reminder of the remarkable intricacies within the world of aviation, a world both intriguing and profound. The flaps and slats on airplane wings play a critical role in enhancing lift, particularly during the phases of takeoff and landing. When deployed, these surfaces change the shape of the wing. Flaps extend downward at the trailing edge, while slats extend outward and forward from the leading edge. This transformation alters the airflow around the wing, creating a more favorable pressure distribution. As the airplane moves at lower speeds during takeoff and landing, the ability to generate sufficient lift becomes essential. The adjustments made by the flaps and slats increase the wing's surface area and maximize the air's interaction with the wing. This allows the airplane to rise more easily from the ground and provides the necessary lift to safely glide back to land. When the airflow is optimized in this manner, the aircraft gains improved stability and control. Pilots can maneuver their planes with heightened precision, even as they operate at reduced speeds. Such enhancements help ensure smoother transitions, allowing for a comfortable experience in the important moments of flight. This delicate interplay of aerodynamic forces reflects the intricate design of wings. The flaps and slats come together harmoniously, showcasing the beauty of physics at work. In this continuous relationship with the air, each flight reveals the wonders of lift, stability, and control, inviting quiet contemplation of the mechanisms that support flight. Hydraulic systems within an airplane are essential for the functioning of control surfaces, such as ailerons and elevators. These systems rely on pressurized fluid to transmit force and enable movement. By maintaining consistent pressure within the system, the aircraft can achieve precise handling and maneuverability. When the pilot inputs a command, such as adjusting the ailerons to roll or altering the elevators for pitch, hydraulic fluid flows through specialized lines and actuators. This fluid acts like a medium, efficiently transferring the force required to move the control surfaces. The careful balance of pressure ensures that even the slightest adjustments by the pilot result in accurate movements of the wings and tail. Throughout the flight, the hydraulic system remains under close monitoring, adapting to varying conditions without compromising performance. The ability to maintain stable pressure is crucial, especially during critical moments of flight, like takeoff and landing. In this continuous dance of fluid dynamics, the harmonious operation of hydraulic systems helps airplanes navigate the skies with grace and control. Each interaction within these systems contributes to the overall stability of the aircraft, reinforcing the intricate relationships between pressure, movement, and direction. Such precision allows for smooth adjustments, inviting thoughts of how seamlessly flight unfolds, carried by the steadfast support of hydraulic power. Air traffic patterns reflect subtle rhythms that change with the seasons. These patterns are shaped by the natural flow of human activity throughout the year. During the summer months, there is typically an increase in air travel, as many take advantage of warmer weather and school holidays. This annual rise brings a notable influx of flights, connecting people to various destinations. Around winter holidays, another peak emerges. Families and friends often reunite during this time, leading to heightened travel demands. The consistent arrival of these seasonal peaks creates a familiar cycle, year after year. Behind this, the infrastructure of air traffic management adapts to these changes. Air routes are optimized and schedules adjusted to accommodate the increased volume. During milder months, flights may spread out more evenly across the days, whereas during peak times, there may be a surge of departures and arrivals, as if echoing the rhythm of life itself. With each passing season, this ebb and flow continues, weaving a pattern that is both predictable and dynamic. As these changes unfold quietly in the background, they contribute to the overall tapestry of aviation, creating a continual dance of movement that persists beyond our sight. Modern commercial airliners, like the Boeing 787, possess impressive capabilities when it comes to travel distances. The maximum range often hovers between 8,000 and 8,500 nautical miles. This range is a product of careful engineering and design, enabling these aircraft to glide effortlessly through the sky for extended periods. With such distances, the 787 is equipped with efficient fuel systems and lightweight materials, allowing for long journeys across vast oceans and continents. Aerodynamic shapes facilitate smooth flight, minimizing resistance and optimizing fuel consumption. Each component, from the engines to the wings, plays a role in achieving this impressive range. As the aircraft traverses the sky, it can comfortably carry passengers over lengthy routes without the need for multiple stops. This capacity for non-stop flights highlights a balance of power and precision that characterizes modern aviation. These soaring machines, with their significant range, continue to redefine air travel, quietly shaping journeys that span great distances. The hum of the engines, the flow of air outside, and the vastness below create a serene atmosphere, cradling all within as they journey through the clouds, ready to reach new horizons. The structural integrity of an airplane, particularly its wings and fuselage, is a masterpiece of engineering precision. These components are meticulously designed to endure significant forces, allowing the aircraft to navigate various maneuvers with stability. The maximum load factor is typically around 3 to 4 times the force of gravity. This means that during flight, when the plane encounters turbulence or changes in direction, its structure can absorb and redistribute these stresses effectively. The wings, stretching outward with graceful lines, are crafted with materials that provide strength while remaining lightweight. They flex slightly under pressure, a feature that enhances their ability to manage the strains of flight. The fuselage, which houses all systems and passengers, is equally fortified, ensuring safety and resilience. The materials used are engineered to maintain their shape and strength, even while experiencing dynamic forces. This thoughtful design allows for a safe and smooth experience in the sky. Every curve and joint within the airplane works in harmony, confirming the safety of the structure as it traverses through the clouds. As the airplane soars, its body stands firm, quietly navigating the balance of forces while maintaining a gentle path through the vast expanse of air, inviting thoughts of distant places and possibilities yet to unfold. Airplanes are built to function within a carefully defined range of temperatures, ensuring their performance remains steady and reliable. And the operating temperatures for most aircraft span from an extreme cold of about -65 degrees Fahrenheit to a warm peak of around 120 degrees Fahrenheit. This range is essential because both very high and very low temperatures can influence various aspects of flight. In the cold, the materials of the airplane respond differently, and the engines rely on precise interactions to function smoothly. The fuel, too, behaves uniquely, requiring meticulous design considerations to maintain proper flow and combustion. The wings, with their aerodynamic surfaces, remain robust yet flexible, adapting to the chilly air that envelops the craft. Conversely, at high temperatures, the effects on performance can also be significant. The air density decreases, which can impact lift and engine efficiency. Structures and systems are engineered to handle these changes gracefully. Each component, from the avionics to the control surfaces, works in harmony, designed to withstand the challenges posed by the environment. Every part of an airplane carries the wisdom of its design, reflecting a careful thought process that ensures functionality across a broad temperature spectrum. As the airplane moves through various climates, it remains a study in resilience, adapting continuously to maintain its journey through the skies, embracing the warmth of the sun and the chill of the high winds with quiet determination. Over time, as airplanes continue their journeys through the skies, the intricate wiring that connects various systems can undergo subtle changes. Each flight exposes these wires to a blend of heat, vibration, and environmental conditions. While these wires are designed for resilience, the constant strain can lead to gradual degradation. This slow wear can occur over many years, as the materials that make up the insulation and connections may weaken. Heat, in particular, affects the performance of these wires, altering their physical properties. While initially robust, the wiring can develop issues that, if left unchecked, might lead to electrical complications further down the line. Regular maintenance plays a crucial role in safeguarding the integrity of these essential components. Scheduled inspections allow for the careful evaluation of the wiring, ensuring that signs of wear are identified early. It is within this routine check that any potential electrical concerns can be addressed, supporting the ongoing health of the aircraft. The careful reflection on these internal systems emphasizes a broader understanding of their longevity. Each component is part of a meticulous balance, ensuring that the airplane remains a reliable vessel through the many seasons it encounters. As time flows gently on, this attention to detail sustains the aircraft's ability to travel smoothly, always ready to embark on the next journey. The sun, a constant presence in the sky, emits a range of electromagnetic radiation that envelops the Earth. This radiation interacts with various materials and systems, including the sensitive components found within airplanes. As these aircraft navigate through the atmosphere, they are inevitably exposed to varying levels of sunlight and its accompanying electromagnetic waves. Over prolonged flights, especially at high altitudes where the atmosphere is thinner, this radiation can impact the delicate balance of an airplane's electronic systems. The continuous exposure may lead to gradual wear on certain components, slowing their response times or diminishing their effectiveness. Sensitive instruments and circuits, intricately woven into the fabric of the airplane, can experience shifts in performance due to this sun-induced stress. Some components might endure these changes gracefully, while others may show signs of malfunction or inefficiency over time. Understanding this interaction helps in monitoring the overall health of the aircraft's systems. It highlights the importance of consistent evaluations and adjustments within the technological heart of the airplane. As these interactions unfold silently, they weave into the tapestry of the airplane's journey, always guiding it gently onward, through sunlight and shadow alike. In the delicate dance of air and material, some airplanes can experience a phenomenon known as catastrophic flutter. This occurs when aerodynamic forces join with the natural frequencies of the airplane's structure, creating a rapid oscillation that can echo through the wings and fuselage. Transitions of air over these surfaces shape an invisible force, acting upon the structure in ways that can lead to unexpected movements. The beauty of aircraft design lies in their carefully calculated balance of materials and shapes, which determine how they interact with the forces of flight. However, under certain conditions, this harmony can give way to instability. Each component vibrates, resonating with its own frequency, and when matched with the external air pressure, a cycle begins. If this flutter persists unchecked, the resulting stresses can accumulate, risking severe structural damage to the airframe. Identifying these patterns is crucial, as early detection can prevent the development of serious issues. The intricate balance of engineering strives to maintain this equilibrium, allowing the aircraft to glide smoothly through the expansive sky. In every flight, layers of design and physics gently intertwine, their effects felt over time, leading the airplane forward through the calm or turbulent currents of the atmosphere. Within the heart of an airplane lies its engines, intricate systems composed of various components, all working in harmony to generate thrust. Over the long periods of operation, these parts endure constant cycles of stress and strain. The intricate dance of air and fuel, along with the sheer forces of movement, leads to a gradual process of wear and tear. As time flows on, the blades within the turbines might experience subtle changes in their surfaces. The metal, though strong, is not immune to the soft erosion caused by the particles that rush past at great speed. This slow degradation can affect their efficiency, as the performance of each component intricately weaves into the overall function of the engine. Small amounts of wear will accumulate, affecting how well everything operates. Changes in performance may need careful monitoring, as they signal the need for maintenance. Regular inspections allow skilled hands to address any issues before they develop further, returning parts to their state of optimal functioning. In this gentle cycle of use and care, engines seamlessly integrate their history into the ongoing flight, quietly driving the airplane forward through vast stretches of sky with quiet determination. Airplane wings possess a carefully designed shape that plays a vital role in their function. This unique structure, known as an airfoil, allows for the smooth flow of air over and under the wings, creating lift as the aircraft moves forward. The gentle curvature on the upper surface and the flatter profile below work together, guiding the air in a way that encourages a difference in pressure, lifting the airplane into the sky. These wings are built with materials that ensure strength while remaining lightweight, contributing to their aerodynamic efficiency. Their design is also responsive to various flight conditions, allowing for stable flight, whether the aircraft is climbing, cruising, or descending. At different speeds and altitudes, the characteristics of lift remain consistent, helping to ensure a smooth journey through the air. As the aircraft navigates through changing weather patterns, these wings adapt naturally, maintaining balance. The ability to experience various forces without compromising their stability illustrates the genius of their construction. Every detail is accounted for in this peaceful ballet of aerodynamics, where the wings quietly do their work, allowing for graceful movement across the expansive sky, ready to meet the journey ahead. Airplane engines function under conditions of extreme heat, operating efficiently at around 1,500 degrees Celsius. This remarkable temperature is essential for the combustion process that powers the engine, fueling the aircraft's propulsion. The materials used in engine construction are carefully selected for their ability to endure such high temperatures. These materials are often layered and treated, providing strength while also allowing for heat dissipation. The design of the engine includes various cooling systems that help maintain structural integrity, ensuring the components remain stable over long periods. Even as they endure thousands of hours of operation, these engines are engineered to maintain performance and efficiency. Their longevity is a testament to the precision of their construction. Each part works in harmonious balance, designed to withstand the stresses and strains of flight. Over time, as the engine operates, small maintenance checks may become necessary, ensuring everything operates smoothly and efficiently. Despite the high temperatures, the sophisticated engineering allows the engine to thrive within its environment. Each cycle through the engine presents an opportunity for exploration as heat and energy transform into motion, continuing the journey through the vast expanse above. Materials in airplane construction are subject to many environmental influences, which can gradually affect their integrity. Exposure to elements such as ultraviolet rays and moisture contributes to a slow degradation process. Over time, ultraviolet light can cause certain materials, especially composites and plastics, to become brittle. This change may lead to a loss of flexibility, affecting the overall strength of the structure. Moisture can also have a softening effect, particularly on metallic components, leading to potential corrosion. Such interactions with the environment are ongoing, creating a need for regular inspections to monitor the condition of these materials. These assessments help ensure that any subtle changes are detected early. As the years pass, routine maintenance may include the replacement of certain components. This process is crucial for maintaining safety and ensuring that performance levels remain high. Each replacement piece is typically selected for its resilience, designed to withstand similar environmental challenges. This careful attention to material condition fosters an enduring strength within the aircraft structure, ready to embrace the skies once again. Sound generated during flight travels through the air, reaching a speed of approximately 343 meters per second when at sea level. This velocity allows sound waves to spread outward from their source, creating a tapestry of acoustic information in the surrounding atmosphere. As these waves move away from the aircraft, they begin to lose intensity. Acoustic energy dissipates, gently diminishing as it propagates through the air. This gradual decay occurs for a variety of reasons. As sound waves travel, they encounter obstacles and variations in air density, which can absorb and scatter their energy. Each interaction, while subtle, contributes to the overall softening of sound as it stretches across distances. With each passing meter, the vibrant tones of flight give way to the quiet embrace of the environment, weaving together the rich background of nature. The beauty of this phenomenon lies in its persistence, even as it fades gently into the distance. The sound of an aircraft, once crisp and clear, becomes a distant whisper, a reminder of the vibrant movement above. In this way, the journey of sound reflects a calming continuity, echoing softly into the tranquil air around, ready for the next moment of quiet exploration. The shape of airplanes, crafted with precision for optimal aerodynamics, is not immune to the passage of time and the forces of nature. Over the years, these graceful structures encounter various environmental factors, such as rain and dust, which gently wear away at their surfaces. This process of erosion, subtle and gradual, alters the fine contours that once offered seamless airflow. As rainwater trickles down the fuselage, it carries with it tiny particles of grit and debris. Each droplet, each speck, contributes to the slow reshaping of the airplane's surface. Dust carried by the wind may settle on wings and tail sections, creating micro-textures that disrupt the originally smooth lines designed to enhance lift and reduce drag. Over time, these accumulated effects can lead to changes in fuel efficiency, as the smooth passage through the air becomes interrupted by imperfections. Flight characteristics, such as maneuverability and stability, may also shift, reflecting the gentle impact of the surrounding environment. This slow transformation speaks to the continuous relationship between an airplane and the natural elements that envelop it, a reminder of the ever-unfolding dialogue between engineered design and the forces at play in the world. The dance of erosion, quiet and unassuming, allows for a sense of calm continuity, reflecting the passage of time in the skies above. Over time, the materials that form the body of an airplane experience a subtle yet significant phenomenon known as metal fatigue. This gradual process results from the repeated stress that occurs during flights. Every ascent, rotation, and descent contributes to cycles of tension that the metal must endure, creating a gentle strain on its structure. Initially, this stress may go unnoticed, as the aircraft appears to maintain its integrity through countless journeys through the skies. However, as the years pass and the airplane continues to traverse great distances, the resilience of the metal begins to wane. Tiny changes may occur, almost imperceptibly, leading the material closer to its limits. In this silent transformation, minute cracks can form, often hidden from view, residing within the very fabric of the aircraft. These cracks reflect the long-term effects of countless flights, gentle reminders of the stresses endured. Though they may start infinitesimally small, these alterations represent the delicate balance of strength and wear, speaking to the endurance of the materials themselves. This ongoing journey of metal fatigue unfolds quietly, echoing the passage of time and the relationship between forces acting on the airplane and the properties of the metals used. Each flight leaves a trace, a small record of endurance that builds over time, leading to an ever-deepening narrative etched within the structure itself. The calm, patient unfolding of this process invites a sense of serenity, emphasizing the continuity of existence within the realm of flight. Within the wings of an airplane, a network of structural beams known as spars plays a vital role in supporting the aircraft. These spars are designed to bear the loads and forces that arise during flight, helping to maintain the overall shape and stability of the wing. Constructed from lightweight materials, they effectively balance the need for strength and structural integrity with the desire for fuel efficiency. This careful selection of materials ensures that the airplane can soar gracefully through the sky without carrying unnecessary weight. The spars work in harmony with the wing's shape, creating a system that allows for optimal performance while minimizing stress. As the airplane travels through the air, these spars endure various pressures, adapting gently to the changing forces. Each flight brings new experiences for the wings, and with each journey, the spars silently contribute to the overall resilience of the structure. This ongoing support highlights their essential role, quietly reflecting the design that enables the airplane to traverse vast distances. The interplay between the lightweight materials and the demands of flight fosters a sense of stability within this intricate framework. Over time, these elements continue to work together seamlessly, ensuring that the wings remain both strong and efficient, ready for every new adventure in the skies. The role of light in aviation is fundamental, as it provides essential visual cues and supports the operation of cockpit instruments. Pilots rely on various sources of light to navigate through different conditions. The clear interplay of natural and artificial light helps them gauge altitude, establish orientation, and communicate important information regarding their surroundings. As visibility gradually decreases, the landscape beyond the cockpit becomes less distinct, presenting a subtle challenge for pilots. In these moments, their reliance on visual references can become more pronounced. Fading daylight or thickening clouds can alter the way the world appears, urging a careful adaptation in flight operations. To enhance safety in such conditions, there are established protocols that guide pilots, ensuring they remain vigilant. The instruments within the cockpit, illuminated by calming displays, provide critical information that allows for continued awareness and assurance amidst changing light levels. In this delicate balance between navigation and visibility, light remains a guiding force. The aircraft maintains its path, a testament to the thoughtful design of its systems, even as the environment shifts gently around it. This continuous flow of information and observation supports the aircraft's journey through the vast skies. In the serene world of flight, the design of airplanes is an intricate balancing act. They are crafted to endure the dynamic forces encountered at high altitudes, where the atmospheric pressures shift remarkably. Each component is precisely engineered to maintain structural integrity, ensuring that the aircraft remains stable and secure during its journey. The fuselage, wings, and tail are built using materials that possess both strength and flexibility. Advanced alloys and composites are chosen for their ability to tolerate significant stress while minimizing weight. This careful selection helps the airplane navigate through turbulent skies while preserving its form over time. As the airplane ascends and descends, it experiences a range of pressures that can fluctuate at different altitudes. Each flight is a testament to the resilience of its structure. The continuous interplay between external conditions and the engineered systems within supports a safe experience throughout its operational life. In this way, airplanes embody a remarkable harmony of design and function, ready to meet the demands of the skies. Their enduring presence serves as a quiet reassurance, allowing for the exploration of vast expanses above the earth. Within the framework of airplane design, philosophies evolve softly, shaped by the rhythm of time and shifting ideals. Over spans of 15 to 20 years, these philosophies transform, echoing the changing preferences of travelers and the guidelines set by environmental considerations. Each cycle invites a fresh look at how airplanes are conceived, balancing efficiency with sustainability Engineers and designers reflect upon past innovations, drawing from a wealth of knowledge. This gradual progression allows for the integration of new materials and technologies that enhance aerodynamics and fuel efficiency. With each wave of change, the essence of flight is reimagined, resulting in structures that are not simply a means to an end, but embodiments of advancement. The interplay between design philosophy and its external influences fosters a gentle evolution. Airplanes become vessels of new ideas, adapting to the whispers of the world around them while remaining steadfast in functionality. This ongoing transition invites a sense of continuity, where every airplane reflects a legacy of progress while looking forward to a future of possibility. A soothing reminder of resilience and adaptation, the spiral of design invites exploration into what comes next. Commercial airplanes possess a wide range of maximum takeoff mass, often varying from 70,000 pounds to well over 600,000 pounds, contingent upon their design and intended use. This variation is a key aspect of their physical structure, reflecting the intricate balance between load capacity and fuel efficiency. Each model is engineered with specific materials and aerodynamic shapes that maximize these characteristics, ensuring flight stability while accommodating a diverse array of payloads. The weight of an airplane impacts many factors during its journey through the sky. Lighter models typically exhibit greater fuel efficiency, allowing them to soar longer distances with less energy expended. Heavier models, on the other hand, may require more robust engines and enhanced structural support, enabling them to carry greater loads without compromising safety or performance. As airplanes evolve, the relationship between their maximum takeoff mass and overall efficiency remains central to their design. This ongoing refinement ensures that each aircraft operates within the parameters set by its physicality, highlighting the delicate interplay between weight and the forces of flight. The calm and steady nature of this engineering process underlines an unbroken continuum of development and adaptation. Each model carries with it not just the potential for flight, but the silent promise of future innovation just waiting to unfold. Aircraft wings are remarkable structures, generating significant aerodynamic forces that play a central role in flight. These forces can lead to a natural bending or flexing of the wings, a process that allows them to absorb stress and enhance overall performance. Engineers carefully design wings with a specific degree of flexibility, tailoring their shape and material composition to adapt smoothly to varying loads and atmospheric conditions. This flexibility ensures that as the aircraft encounters changes in speed or turbulence, the wings can shift slightly without compromising their structural integrity. Such resilience is crucial for maintaining strength over long periods of use, allowing the wings to withstand the repetitive stresses of flight. The careful balance between strength and flex is a testament to the thoughtful engineering involved in aircraft design. Over time, this adaptable nature not only contributes to a smoother ride, but also extends the lifespan of the wings. As the plane navigates through diverse environments, the ability to flex enhances safety and reliability. The wings dance gently in response to the forces acting upon them, an elegant testament to the harmony of engineering and physics that sustains flight. Each flight is a continuation of this quiet interaction, a serene cycle of motion and stability ready to unfold once more in the expansive sky. In the journey through the skies, motion creates a gentle yet persistent aerodynamic drag. This drag arises as the aircraft moves through the air, interacting with the molecules that surround it. The shape of the aircraft influences how this drag behaves, impacting fuel efficiency as it glides through the atmosphere. Each curve and angle of the wings, as well as the body of the aircraft, is designed to manage this drag thoughtfully. The interplay of air on the surface can either create resistance or allow for a smoother passage. As technology progresses, engineers continually refine designs to minimize this drag. Every small adjustment can lead to substantial long-term benefits in fuel consumption. These enhancements do not just improve the dynamics of flight, they contribute to a more efficient use of energy over time. With ongoing improvements, each innovation represents a step toward a quieter, more efficient interaction with the environment. The aircraft persists in its dance through the air, a subtle reminder of the ongoing harmony between motion and design, flowing effortlessly as it moves onward through the vast expanse. Every aircraft has a minimum flight speed, which is often referred to as stall speed. This speed varies among different types of airplanes, but for small aircraft, it generally falls within a range of about 60 to 80 knots. Maintaining speed above this threshold is essential for consistent lift. When flight slows below this critical limit, the wings can no longer sustain the airflow necessary to keep the plane aloft. At this point, the aircraft may begin to lose altitude, gently descending as the lift diminishes. Each wing, with its specific design, works to provide the necessary aerodynamics for safe flights. The interaction between speed and lift becomes a delicate balance. Under ideal conditions, as speed increases, the lift generated by the wings can counteract the weight of the aircraft, allowing it to soar gracefully through the air. Understanding this delicate relationship helps frame the flight dynamics, emphasizing the importance of speed in maintaining stability and control. In this serene navigation across the sky, the interplay of speed and lift ensures a gentle and steady voyage, echoing the tranquility of flight. In the realm of aviation, the Dutch roll phenomenon stands out as a unique type of oscillation that may arise in certain airplane designs. This gentle movement consists of a combination of yaw and roll, creating a rhythmic motion that can sway the aircraft side to side. It's as if the airplane is engaging in a soft dance, its wings tilting slightly while the nose shifts from side to side. This behavior occurs due to the interaction between the aircraft's wings and stabilizing surfaces. When there is a disturbance, such as a gust of wind, the aircraft may begin to yaw away from its intended path. The response induces a roll, which in turn can create a back and forth motion. Such oscillations are subtle, yet can lead to challenges for pilots. To navigate through a Dutch roll, specific techniques are employed, allowing for calm adjustments to regain stability. With practice, pilots learn to respond gently, guiding the aircraft back to a steady course. This oscillation serves as a reminder of the intricate dynamics at play in flight, where each movement can influence the journey, creating a continuous flow of motion as the airplane glides through the expansive skies. In the delicate art of airplane construction, materials play a crucial role in ensuring longevity and resilience. Aluminum, widely used in the structure of aircraft, possesses remarkable properties that help it withstand the effects of time and the elements. Its lightweight nature contributes to fuel efficiency, while its naturally occurring oxide layer serves as a barrier against corrosion, allowing the aircraft to endure in various environments. Titanium, another essential material, complements aluminum with its own unique benefits. Known for its strength and resistance to corrosion, titanium enhances structural integrity and helps maintain safety over extended periods. The combination of these materials leads to a robust framework that can withstand the varied conditions faced during flight, from humid coastal areas to icy altitudes. Over time, the careful engineering of these materials supports the aircraft as it gracefully travels through the sky. The enduring nature of aluminum and titanium allows airplanes to maintain their performance and shape, ensuring they are well prepared for countless journeys. Through the years, these materials work harmoniously, quietly standing the test of time, ready for the next gentle glide through the heavens. In the realm of aircraft design, the choice of materials profoundly influences their ability to endure. Carbon fiber composites stand out for their remarkable characteristics. Crafted from intertwined strands of carbon, these materials possess an exceptional combination of strength and lightness. Over time, they have shown an impressive capacity to retain their mechanical properties, meaning they can withstand the forces exerted during flight without significant degradation. This resilience is particularly noteworthy as carbon fiber composites are subjected to various environmental factors. Though exposure to sunlight and moisture can affect some materials, these composites maintain their integrity, showing limited wear even after prolonged use. This stability contributes to their effective performance, allowing airplanes to operate consistently through changing conditions. As days turn into years, the enduring qualities of carbon fiber composites form a reliable backbone that supports the structure of the aircraft. They remain steadfast, quietly ensuring everything holds together, ready for the next gentle journey through the skies, resting in the beauty of their engineered simplicity. Wind shear is an intriguing phenomenon, characterized by sudden changes in wind speed and direction. These shifts can occur at different altitudes and have a significant influence on the stability of an aircraft in flight. In many cases, the nature of the wind can transform abruptly, creating challenges for maintaining smooth and steady control. The gentle flow of air surrounding the wings can become turbulent in a moment, altering how the aircraft responds. As time flows on, pilots encounter a variety of environments where wind shear is present, particularly in regions with complex weather patterns. The experience of dealing with such changes can hone their skills and awareness. Extended exposure to these conditions aids in developing an intuitive understanding of the aircraft's responses, encouraging adaptability and resilience in varied flying situations. Training may evolve alongside new insights into atmospheric behavior, ensuring that pilots feel confident navigating through these shifts. This ongoing process unfolds quietly in the background of aviation, enhancing both knowledge and readiness for the dance of the winds, softly whispering their secrets to the skies. Internal fuel tanks in airplanes are remarkable structures, crafted to endure the high pressures associated with aviation. These tanks serve an essential function, allowing for the efficient storage of fuel while minimizing the risk of leaks. The materials used in their construction are selected carefully, taking into account their ability to withstand the stresses of flight. Over time, the design focuses on resilience, ensuring that external forces do not compromise the integrity of the tanks. Corrosion resistance is a key aspect of this design. Factors such as moisture and temperature fluctuations, which can occur at high altitudes, are considered during the engineering process. Each material is chosen for its ability to resist degradation over years of service, promoting long-lasting safety. Material fatigue is also a crucial consideration, as repeated cycles of pressure and temperature can wear down even the strongest components. Through a combination of advanced technology and thoughtful material selection, these fuel tanks continue to play a vital role in maintaining the safety and reliability of flight. Their enduring nature allows aircraft to soar, connecting distant places while remaining steadfast in their purpose, quietly functioning beneath the skin of the airplane. Airplanes traverse great distances at remarkable speeds, exposing them to substantial changes in thermal energy. As they ascend and descend through the atmosphere, temperatures can shift dramatically, affecting the materials that make up their structure. Engineers consider these fluctuations very carefully, designing components that can withstand both heat expansion and contraction. This ensures that the airplane's structure remains stable and intact despite the varying temperatures encountered. Materials selected for construction possess specific thermal properties, allowing them to respond to heat changes without losing strength. Each part is engineered to flex gently in response to temperature variations, absorbing stress while maintaining shape. Careful attention is paid to how these materials interact with each other, as well as how they perform under extreme conditions found at high altitudes. By integrating these thoughtfully chosen materials, airplanes achieve a balance that supports their overall integrity. This careful design fosters a steady resilience, enabling the aircraft to endure the shifting pressures of high-speed travel. Such resilience quietly underpins every flight, allowing the airplane to embrace the challenges of the skies with a sense of calmness. Airplane technology evolves through a gradual yet significant pattern, reflecting advancements over time. The journey of flight has seen major breakthroughs occurring roughly every 20 to 30 years. During these intervals, fundamental changes reshape the landscape of aviation. For instance, the transition from propeller-driven aircraft to jet engines represents one of these pivotal moments. This shift illustrated an important development in aerodynamics and propulsion. Jet engines harness the principles of jet propulsion, enabling airplanes to travel faster and more efficiently. The underlying structures of these engines, featuring sleek designs and powerful components, work harmoniously to maximize thrust while minimizing drag. Each advancement builds on the knowledge accumulated from previous generations, allowing for stronger materials and improved aerodynamics. As technology progresses, observable changes ripple throughout the plane's configuration, optimizing performance and reliability. Periodic innovations are layered upon one another like gentle waves, creating a continuous evolution that enhances the capabilities of flight. Each new design maintains a connection to the past while also reaching towards the future, poised for the next chapter in this unfolding story. Pressure changes at various altitudes significantly influence the way fuel and air mix in engines, guiding the efficiency and performance of aircraft. As an airplane ascends, the atmospheric pressure decreases, altering the density of the air. This change affects how oxygen enters the engine, modifying combustion characteristics. The intricate balance between fuel and air remains crucial for optimal operation, and at different heights, this relationship shifts gently, adapting to the thinner atmosphere. Long-term exposure to these fluctuating pressures impacts engine components over time. Constantly moving through varying altitudes subjects materials to stress, leading to gradual wear. Metal parts, seals, and other components experience shifts in temperature and pressure, prompting them to expand and contract subtly but steadily. This cycle can create fatigue, influencing the lifespan of engine elements. Understanding these responses contributes to enhancing engine designs and materials, fostering resilience against the natural forces at play. The ongoing interplay between pressure and engine performance continues as a soft reminder of the complexities involved in flight, quietly embracing the delicate balance required for sustained operation in these dynamic environments. Cruising at heights ranging from 30,000 to 40,000 feet, Commercial airplanes find a sweet spot in the atmosphere where conditions favor efficient flight. At these elevated altitudes, the air thins noticeably. This reduced air density leads to lower drag on the aircraft, allowing it to glide more smoothly through the skies. In this serene expanse, engines can operate efficiently, utilizing fuel in a way that maximizes distance traveled while consuming less. The thin air creates a lighter environment, contributing to a steady airflow over the wings and fuselage. As the aircraft moves forward, this gentle stream enhances lift, supporting the airplane's weight with greater ease. The balance between lift and drag becomes vital, and the serene altitude offers a kind of harmony in flight. Over time, this delicate equilibrium results in optimal fuel consumption and allows for longer journeys without the need for frequent stops. The airplane remains cradled in a peaceful drift, embodying the artistry of aerodynamics and engineering as it navigates the quiet expanse above, keeping pace with the rhythm of the atmosphere surrounding it. The outer shell of an airplane is constructed from sturdy materials like aluminum or advanced composites. This strong framework serves an essential role, helping the aircraft endure the varying pressures it encounters during flight. As it ascends and descends through different layers of the atmosphere, the pressure around the airplane changes significantly. The robust design of the shell ensures stability, protecting the delicate systems within from these fluctuations. Aluminum and composites both possess natural resistance to corrosion, which is beneficial for longevity. This resistance helps maintain the structural integrity of the airplane over many years. The outer shell remains resilient against the elements, allowing it to face rain, ice, and other atmospheric factors with ease. Within the calm presence of the aircraft, the materials work harmoniously to ensure that every journey is safe and sound. Over time, this careful balance of strength and durability allows airplanes to complete numerous flights while retaining their essential qualities, continuing to glide through the skies with unyielding grace. Airplanes exist within a larger context that cycles through phases of economic change. This economic cycle affects the level of demand for air travel, shifting gradually every 7 to 10 years. During periods of growth, more people are inclined to travel, increasing the flow of passengers across the skies. Airlines then mobilize their fleets to meet this rising interest, ensuring that their aircraft are ready to soar. As the cycles ebb and flow, some years may see an increase in travel, while others may result in a decrease, reflecting broader economic conditions. These fluctuations impact airline profitability, as demand for available flights is influenced by various factors, including financial stability and global trends. Through these ongoing cycles, airplanes are designed to remain durable, able to withstand not only the physical elements of flight, but also the rhythms of the economy they inhabit. This gentle dance of demand and supply allows aircraft to adapt and endure, continuing their essential role in connecting distant places over the vast expanse of the skies. Airplanes, while soaring gracefully through the atmosphere, encounter various environmental elements that can lead to the buildup of static electricity. This charge can accumulate from the friction between the aircraft's surface and the air itself. Generally, under normal conditions, this charge is minimal and does not pose significant risks. However, awareness of its presence is crucial, especially during critical operations such as refueling. Procedures are carefully established to manage this static charge. During refueling, measures are in place to safely discharge any accumulated electricity, ensuring that the airplane remains free from potential electrical hazards. Grounding methods are commonly employed, gently guiding excess charge away from sensitive systems. This thoughtful management reflects the intricate balance of physical properties at work within and surrounding an airplane. The systems that govern the safety of these aircraft operate quietly, allowing for a serene journey from one destination to another, while maintaining vigilance against unseen forces. In this way, the harmony of flight continues, ready to embrace the next chapter of its existence in the vast open sky. Engines on airplanes harness the principle of thrust to navigate the vast skies. When fuel is burned, it transforms into exhaust gases, which are expelled rapidly backward. In this process, something remarkable occurs. For every action, there is an equal and opposite reaction. The release of these gases generates thrust that moves the airplane forward with efficiency and grace. This conversion of fuel into kinetic energy is not only fundamental, but essential for long-distance travel. It allows airplanes to cover great distances with remarkable speed. The internal mechanisms of the engines work in harmony, drawing in air, compressing it, mixing it with fuel, and igniting the mixture. Each phase is a delicate dance of physics, seamlessly transforming chemical energy into motion. As the engine hums steadily, it carries the airplane onward, creating a sense of flow that glides through the atmosphere. This continuous process keeps the aircraft aloft, a testament to the elegance of natural laws at play within the confines of metal and fuel. In such a quiet, rhythmic way, the journey unfolds, connecting distant places beneath a blanket of stars, patiently awaiting the next horizon. In the construction of aircraft, materials such as carbon fiber and aluminum alloys are chosen with great care. These materials are engineered to provide a remarkable balance of strength and lightness, known as strength-to-weight ratios. This balance is essential as it allows the aircraft to withstand the forces encountered during flight while keeping its overall weight to a minimum. Carbon fiber, with its woven structure, is incredibly strong, yet very light. Its properties enable it to endure stress and strain without adding unnecessary heaviness. Aluminum alloys, similarly, provide an impressive strength while maintaining the essential lightness required for aerial travel. The combination of these materials creates a framework that not only supports the aircraft during flight, but also contributes to its long-lasting performance over many journeys. The thoughtful selection and integration of these materials ensure that the aircraft remains durable through varied conditions. With each component working in harmony, the structure retains its integrity and resilience, allowing it to thrive in the skies. The interplay of strength and weight continues to support the aircraft as it glides gracefully, ready to embrace the next adventure in the serene expanse above. At high speeds, a fascinating phenomenon known as aileron reversal can arise in certain aircraft. Under specific conditions, the ailerons, which are designed to control the roll of the airplane, may behave in an unexpected manner. Instead of generating a desired effect of banking or tilting, they can inadvertently produce the opposite response. This curious behavior stems from the complex interactions between airflow and the design of the ailerons themselves. When an aircraft approaches greater velocities, the aerodynamic forces acting upon it change in significant ways. The flow of air over the wings and control surfaces alters, creating scenarios where the ailerons generate counterproductive lift. As a result, instead of rolling the airplane in the intended direction, the aircraft may start to roll in a manner contrary to the pilot's commands. This delicate balance between speed and control can introduce challenges, particularly during tight maneuvers. Understanding this condition is essential for the design and construction of aircraft, further showcasing the intricate relationship between aerodynamics and structural engineering. Within the quiet framework of flight, these phenomena remind us of the delicate interplay of forces that allows an airplane to soar through the skies. A gentle exploration of these attributes fosters a deeper appreciation for the science guiding flight, keeping the sense of wonder alive as it floats seamlessly through the vastness above. Occasionally, stall conditions can arise in aircraft, which might not only be due to a straightforward loss of lift. In certain situations, factors such as asymmetric ice accumulation on the wings can also play a significant role. This occurs when ice forms unevenly on the surface, disrupting the smooth flow of air over the wings. The uneven distribution of ice can lead to a situation where one wing produces normal lift, while the other struggles, increasing the potential for control difficulties. When this imbalance occurs, the aircraft becomes more susceptible to stalling. In stable flight, even a small change in aerodynamics can result in unexpected behavior. As the airflow around the wings is altered by the presence of ice, the lift produced can diminish, leading to complications that may require careful management. The consequences of such conditions mean that pilots must remain vigilant, as careful handling becomes essential when grappling with these unusual challenges. This delicate interplay highlights the numerous factors affecting aircraft performance. By understanding these characteristics, one can appreciate the complexity of flight that exists even beyond the cockpit, encompassing the wing's interactions with the surrounding environment. With each passing moment, the dynamics of flight carry on, weaving an intricate tapestry of engineering and natural forces, quietly sustained in the tranquility of the skies. At high altitudes, the air becomes increasingly frigid, often reaching temperatures around -60 degrees Celsius. This stark chill envelops the aircraft as it soars above the clouds. Yet, within the cabin, a comfortable environment is carefully maintained, thanks to sophisticated insulation and heating systems integrated into the craft's design. These systems work diligently to counteract the extreme cold of the outside atmosphere. The insulation serves as a protective barrier, preventing the biting cold from penetrating the interior. Layers of materials, carefully chosen for their thermal properties, work together to keep the cabin warm. Meanwhile, the heating systems circulate warm air, offering a soft embrace against the cold outside. This balance allows passengers and crew to experience the wonders of flight without the discomfort of the harsh conditions beyond the aircraft's shell. As the plane glides through the sky, it becomes a haven of warmth and tranquility, rising above the icy expanse with quiet grace. The interplay of temperature and engineering unfolds continuously, contributing to a serene journey through the vast, chill blue of the upper atmosphere, where the only sound is the gentle hum of the engines and the rhythmic flow of air outside. Airplanes are designed with a thoughtful layer of insulation material nestled between the interior cabin and the exterior shell. This layer plays a crucial role in managing the temperature inside, allowing for a stable and pleasant environment during flight. It works by trapping air, an effective insulator that helps to reduce the transfer of heat between the cold outside and the warmer space within. Beyond temperature regulation, this insulation also helps to prevent condensation, which can form when warm air meets the cool surface of the aircraft's outer skin. By minimizing moisture buildup, it contributes to the overall comfort and integrity of the cabin throughout many flights. This balance of air temperature and humidity creates a serene atmosphere for those aboard. Day after day, as aircraft ascend into the vastness of the sky and return to solid ground, the insulation quietly fulfills its purpose. This reliable layer effectively supports the dynamics of flight, allowing for uninterrupted journeys through changing weather patterns and altitudes. Each layer of insulation harmoniously integrates into the aircraft, emphasizing the importance of keeping the cabin environment just right, open and easing towards the next flight ahead. Airplane runways endure a steady rhythm of activity, witnessing countless landings and takeoffs each day. Over time, this constant use places stress on their surface, leading to gradual wear and tear. Environmental factors also play a significant role in their degradation. Rain, snow, and fluctuations in temperature can cause elements within the runway materials to contract and expand, resulting in small cracks. These cracks slowly grow as time progresses, sometimes leading to uneven surfaces that can affect the smoothness of the runway. The materials, typically a blend of asphalt and concrete, are designed to withstand many years of such stresses, yet they still require attention. Routine maintenance ensures that any damage is assessed and repaired promptly. Careful inspections and necessary repairs help restore the integrity of the surface, allowing the runways to remain safe and functional. This cycle of use, wear, and careful restoration is part of how runways continue to serve their role in aviation, quietly supporting the rhythm of flight as they blend into the landscape, ready for the next journey to unfold. The cabin atmosphere within an airplane is carefully pressurized, creating an environment that feels comfortable for those aboard. This pressurization is essential, especially at high altitudes, where the external air pressure drops significantly. At such heights, the body can experience discomfort or strain if the cabin pressure does not match the needs of passengers and crew. To maintain a pleasant atmosphere, the internal pressure must be regulated continuously throughout the flight. The airplane's systems actively monitor the pressure levels, ensuring they remain stable and within a safe range. This regulation allows for a sense of ease and relaxation during the journey, enabling the body to acclimate to the altitude without distress. The materials and construction of the aircraft are designed to support this pressurized environment, with strong seals and structural integrity playing important roles. Each component works in harmony to create a balanced atmosphere, contributing to overall comfort. As the aircraft soars through the sky, its systems quietly and efficiently maintain this delicate equilibrium, allowing for a peaceful experience at cruising heights, where the outside world feels distant and serene. This gentle balance of pressure continues as the flight unfolds in the vastness above, inviting tranquil thoughts and restful moments. Fuel efficiency technologies in aircraft have quietly evolved, leading to significant improvements over the years. These advancements gently enhance the way airplanes perform, allowing them to glide smoothly through the sky with less energy consumption. Every component, from the engines to the aerodynamic shape of the wings, contributes to this efficiency, working in unison to optimize fuel use. Newer materials are often lighter yet stronger, reducing the overall weight of the aircraft. As the design of engines becomes more refined, they harness energy more effectively, translating into lower fuel needs. This not only encourages better performance, but also aids in minimizing the emissions released into the atmosphere. The harmonious integration of these technologies contributes to sustainable long-term flight practices. As time progresses, aircraft continually evolve, reflecting a steady commitment to reducing their environmental footprint. Even as they ascend into the vastness, the improvements remain a whisper of progress, quietly working to enhance both performance and the tranquility of the journey overhead. This seamless blend of engineering, and nature continues, guiding the aircraft through the serene skies above. The gentle interaction between air and the surfaces of an airplane gives rise to turbulence, an ever-present phenomenon as flights traverse the sky. As planes advance through the atmosphere, air flows around their wings and fuselage, creating patterns of movement that shift and change. This flow is not uniform. Instead, it oscillates in response to the shape of the aircraft and the speed of travel, leading to delicate disturbances. Over time, these disturbances subtly influence the material integrity of the wings and fuselage. The continuous friction and vibration from the air can lead to microscale changes, gently eroding surfaces. Tiny particles may be displaced, and the materials can begin to wear, gradually shaping the surfaces into smooth contours that reflect years of flight. Despite this slow and often unnoticed process, the resilient materials used in aviation are designed to withstand such effects for extended periods, maintaining their structural strength. This ongoing relationship between air and aircraft is a testament to the dynamic forces at play, carrying on through countless journeys, while the soft embrace of the atmosphere surrounds it all. Lift is created by the delicate balance of air pressure above and below an airplane's wings, a subtle interplay that allows the aircraft to rise gracefully into the sky. The unique shape of the wings, often curved on top and flatter underneath, plays a crucial role in shaping this pressure difference. As the airplane moves forward, air splits and flows around the wing. The air traveling over the curved upper surface moves faster than the air beneath, leading to a lower pressure above the wing and a higher pressure below it. This difference is a key factor in generating lift. As the wing encounters this variable airflow, the higher pressure underneath pushes upward, gently lifting the airplane into the air. The smooth and steady interaction of air molecules with the wings creates a consistent force that can sustain flight. This process is a reflection of the harmonious balance found in nature, where shapes and movements work together to create a sense of stability. Each flight is a demonstration of this quiet dance, where the craft remains buoyed by a carefully orchestrated relationship with the surrounding air, continually inviting exploration of the skies above. The landing gear serves as a fundamental component of an airplane, designed with sturdy metals that possess the ability to absorb the shock of landing. These metals are chosen for their strength and durability, allowing them to withstand the forces experienced during each descent. As the airplane touches down, the landing gear compresses and flexes slightly, gently dissipating the energy of the landing impact. This robust structure is built to endure countless cycles of landings and takeoffs, reflecting a quiet resilience that is crucial for safety. Over the lifespan of the aircraft, the materials of the landing gear maintain their integrity, resisting wear and tear as they adapt to repeated stresses and strains. Every landing, with its own unique dynamics, is met with the reliability of this carefully engineered system. The landing gear, almost unnoticed in its daily function, plays a silent yet vital role in the overall harmony of flight. Each time the wheels connect with the runway, they bring a sense of stability and security, a grounding force that ensures a smooth conclusion to the journey. The cycle of flight can continue, assured in the steadfastness of this essential component. The fuel tank of each airplane is commonly situated within the wings, a design choice that optimizes aerodynamics and balance. Constructed from specialized materials, these tanks are engineered to resist corrosion and prevent leaks, ensuring a secure containment for the fuel. This careful attention to the selection of materials contributes to the long-term safety and stability of the aircraft. Throughout its operational life, the tank endures pressure fluctuations and temperature variations, all while maintaining structural integrity. The materials used are not only tough, but also flexible, allowing them to adapt to the stresses of flight without compromising their protective qualities. As fuel is drawn from the tank during the flight, the design ensures that it remains securely contained, minimizing risks associated with leakage. The tank's reliable construction is a silent guardian, working quietly behind the scenes to support the engine and contribute to the overall performance of the airplane. Each flight unfolds with the assurance that the fuel tank, nestled within the wings, stands strong, accommodating the rhythms of air travel with calm and steadfast reliability. Engines of airplanes are marvels of engineering, designed to transform fuel into the power that propels them through the skies. However, as time passes, these intricate machines slowly accumulate dirt and other deposits. These particles can settle within the engine components, subtly affecting their performance. Over the course of many flights, the buildup can lead to a gradual loss of efficiency. To maintain optimal operation, the engines require regular maintenance. This process often involves cleaning certain parts and, when necessary, replacing components that have worn down. Careful attention to these details ensures that engines continue to run smoothly, preserving their ability to generate the thrust needed for flight. The maintenance routines are conducted in structured intervals, allowing the engine to receive thorough care. This diligence protects the heart of the aircraft, keeping it vibrant and ready for takeoff. The gentle rhythm of this care echoes the natural cycles of life, a reminder of the importance of nurturing systems over time. With each inspection and adjustment, the engine remains a reliable force in the dance of air travel, quietly prepared for the next journey ahead. The aerodynamic shape of an airplane is a delicate balance of design and function, allowing it to slice through the air with grace. Over the years, this shape may subtly transform due to small dents or surface erosion, and these changes often occur gradually, almost imperceptibly, as the airplane encounters various elements during flights. The smooth surface, initially crafted to optimize airflow, can become marred by tiny imperfections that develop over time. Even the smallest deviation can disrupt the laminar flow of air, which is crucial for maintaining efficiency. As these alterations accumulate, the airplane's ability to glide effortlessly through the atmosphere may diminish. This gradual shift can lead to increased drag, which in turn affects fuel consumption during flight. Each tiny detail contributes to a complex interaction with the surrounding air, working in harmony to ensure flight stability. While these changes may seem minor, they remind us of the long-term relationship between structures and the forces they face. The resilience of aircraft design aims to adapt and evolve, fostering a continuous journey through the skies, prepared for whatever awaits ahead. Regulatory changes in the aviation industry emerge through a gradual cyclical process, typically spanning 5 to 10 years. This rhythm often reflects the need to address safety incidents or shifts in public policy that arise over time. Each cycle is a response to the evolving nature of air travel and its complexities. When an event occurs that highlights a potential risk, it can spark a thorough examination of existing regulations. Such moments prompt organizations to reassess the guidelines intended to protect both aircraft and passengers. New data from safety incidents can guide changes, revealing areas where enhancements may be necessary. Public policy shifts, influenced by advancements in technology or changes in societal expectations, can also play a role in this cycle. As the world changes, so too do the frameworks that support aviation. These regulations ensure aircraft remain safe and reliable, adapting to meet the ongoing challenges presented by flight. Through this ongoing process, the aviation landscape quietly transforms, maintaining a focus on safety and innovation. Changes unfold seamlessly, like a gentle breeze guiding an airplane across the sky, ensuring its future in a continuously evolving environment. With time, the paint on airplanes experiences a gentle fading, influenced by factors such as sunlight and harsh weather conditions. The ultraviolet rays from the sun contribute to a gradual breakdown of the paint's pigments, dulling vibrant colors and altering the airplane's appearance. Rain, snow, and wind also play their part, wearing away the surface over the years. This slow, ongoing process is a reminder of the environment's persistent effects. Each flight exposes the aircraft to various elements, from strong winds at high altitudes to the intensity of heat on the ground. These interactions create subtle changes that accumulate, gradually transforming the exterior. As the paint wears and loses its protective qualities, it may no longer shield the underlying materials effectively. This deterioration highlights the importance of maintenance, as protecting the aircraft's structure becomes essential for longevity. Regular inspections can identify when it becomes necessary to refresh the paint, restoring both its appearance and the underlying safety features. Such cycles of renewal are part of the natural ebb and flow of an airplane's existence, quietly intertwining with its journey through the skies. The fading paint, while a sign of time passing, serves as a gentle reminder of the care taken to preserve the beauty and integrity of flight. Routine maintenance practices play a vital role in sustaining the reliability of an airplane's systems, particularly the engines and control surfaces. These components, essential for flight, endure the demands of each journey, experiencing fluctuations in temperature, pressure, and mechanical stress. Over time, this can lead to subtle wear that, if left unaddressed, may affect performance. Regular inspections allow for the careful monitoring of these systems, identifying any signs of fatigue or deterioration. Technicians follow detailed procedures, examining the engines for efficiency and checking control surfaces for alignment and responsiveness. This attentive care involves replacing worn parts and lubricating moving elements, ensuring that everything continues to function harmoniously. Such maintenance routines create a sense of stability within the complex systems of an aircraft. They nurture the intricate balance required for safe and smooth operation, allowing the different parts to work together seamlessly. Over time, this careful oversight contributes to a deeper assurance in the integrity of the airplane as it glides through the skies. Each scheduled checkup is a quiet affirmation of reliability, gently preserving the delicate dance of mechanics that allows flight to continue peacefully. In the cockpit, instruments and displays are carefully crafted from durable plastics and robust glass materials. These components are designed to withstand the challenges of flight, ensuring they remain reliable even under varying conditions. The constant pressure of altitude, the vibration from the engines, and temperature shifts are all factors that these materials must endure. Each gauge, each screen provides essential data that pilots depend on, conveying important information in a clear manner. Over time, the resilience of these components allows them to maintain accuracy, helpful even during the long hours of operation. The choice of materials such as specially treated glass helps in minimizing glare, allowing for easy readability in different lighting conditions. This thoughtful design and construction foster a sense of trust in the cockpit's instrumentation. They serve as a steady presence, providing vital insights with unwavering consistency. Each display and instrument is a part of a larger system, harmoniously working together to create a reliable environment for those who navigate the skies. The calmness of these components, built to last, assures smooth communication of data, quietly contributing to the overall experience of flight. The wings of an airplane play a crucial role in generating lift, a fundamental force necessary for flight. This lift arises from the wing shape, often referred to as an airfoil. As air moves over and under the wing, the unique contour creates different pressures on each side. The upper surface of the wing is typically curved, while the lower surface remains flatter, which contributes to this pressure difference. The angle of attack, which is the angle between the wing and the oncoming airflow, further influences this phenomenon. A proper angle allows the wings to optimize the airflow, enhancing lift generation. Under various flight conditions, this pressure differential remains relatively stable. However, it can experience subtle changes due to variations in airflow. Factors such as turbulence or changes in airspeed can slightly modify these pressure zones. These dynamics foster a consistent environment for the aircraft to maintain elevation. Such complex interactions occur seamlessly, creating a tranquil balance that allows the plane to soar through the skies with gracefulness and stability. The wings, in conjunction with their design, stand as a testament to the serene efficiency of flight, providing a gentle reminder of nature's principles as they quietly support the aircraft in its journey above the earth. Radio waves, essential for both communication and navigation, travel through the atmosphere with remarkable speed. These waves, which are a part of the electromagnetic spectrum, can sometimes encounter variations in the atmosphere that influence their behavior. One significant factor is humidity. When the air becomes more saturated with moisture, it can alter the path and strength of radio signals. Higher humidity introduces more water vapor into the air, which can absorb and scatter these waves. This interaction can lead to fluctuations in the clarity and reliability of the signals transmitted. Such changes may occur gradually as the atmosphere shifts throughout the day or in response to weather patterns. Over time, this might affect how effectively a signal can be received, particularly at certain frequencies. Similar alterations can happen due to other atmospheric conditions like temperature and pressure shifts. These variables create a dynamic landscape for radio waves as they travel. Despite these fluctuations, the fundamental properties of radio waves remain consistent, allowing them to navigate through an ever-changing environment, maintaining their role in facilitating connections within our world. The gentle flow of their passage through the atmosphere embodies a serene persistence, ready to adapt to each unique condition as it unfolds. The flight control systems in airplanes possess a remarkable level of redundancy, a fundamental feature that contributes significantly to their long-term reliability. This means that if one component of the system encounters an issue or malfunctions, the overall functionality is not hindered. Instead, alternative mechanisms are in place to ensure continuous operation. Each element within these systems is designed to work in harmony with others, creating several layers of backup. This careful engineering allows the components to support one another. The results of this thoughtful design enhance stability and confidence in flight. The various sensors, actuators, and computers communicate seamlessly, constantly monitoring their conditions. Should a failure occur, the redundant systems can quickly take over to maintain control over the aircraft. This inherent capability of flight control systems is a testament to the harmony of engineering and natural laws. It reflects an understanding of the need for safety and reliability in an environment subject to numerous variables. Through their robust structure, these systems manage to remain steadfast, ensuring that even in the face of challenges, they can adapt and sustain their essential functions, navigating the vast skies with grace and reliability. Maintenance schedules for aircraft are carefully structured around long-term cycles that reflect the intricacies of their operation. Each aircraft has a defined timeline for essential checks and overhauls, usually occurring every 5 to 10 years, based on the frequency of use and the regulatory standards set forth by governing bodies. These cycles are designed to ensure that each aircraft remains in optimal condition over its service life. During these scheduled inspections, different aspects of the aircraft are closely examined. Systems such as engines, avionics, and structural integrity undergo thorough evaluations. Components may be replaced or repaired, allowing for a comprehensive revitalization of the aircraft. This ongoing care helps to identify wear and fatigue that can develop over time, ensuring safety and reliability. Throughout this process, a meticulous record is maintained, documenting each step in the aircraft's maintenance history. This information forms a vital part of understanding the aircraft's condition and is integral to managing its performance over the years. With this tranquil yet diligent routine, the integrity and readiness of the aircraft are preserved, allowing it to soar through the skies with continued assurance. In this way, the rhythm of maintenance intertwines with the passage of time, creating a seamless flow of care and reliability. The maximum takeoff weight of a Boeing 747 is approximately 987,000 pounds, a figure that establishes an important boundary for the aircraft's performance. This weight is the sum of the plane itself, along with fuel, cargo, and passengers. Each of these elements contributes to the elegant balance required for successful flight. As fuel is consumed during a journey, the overall weight gradually decreases, allowing the aircraft to glide through the skies with increasing efficiency. The structure of the 747 is meticulously designed to support this substantial weight, featuring engineering that distributes stress evenly across its wings and fuselage. The wings, crafted with precision, not only provide lift, but are also essential in managing the pressures and forces experienced during flight. Within this framework, careful calculations determine how much can be carried without exceeding limits. The specifications of materials and design ensure that the aircraft remains stable and safe throughout its journey. This delicate interplay between weight and balance sustains the aircraft's capabilities, allowing for a smooth ascent and glide through the atmosphere. Presently, the vast expanse of the sky awaits each Boeing 747, poised for its next tranquil voyage, while the figures of weight and lift continue their silent dance in harmony with the laws of nature. Airlines encounter natural cycles of fleet renewal, often occurring every 15 to 20 years. This rhythm is influenced by the evolving demands of efficiency and technological advancements. As aircraft age, their performance may gradually decline, prompting considerations for replacement. Newer models typically offer enhanced fuel efficiency, reduced emissions, and improved aerodynamics. These characteristics contribute to a more sustainable approach over time, allowing each phase of renewal to reflect the ongoing progress in aviation technology. In this process, the structural integrity of the existing fleet is assessed carefully. With each model, engineers analyze performance metrics, operational costs, and maintenance needs. Over time, the materials used to construct these aircraft have advanced, incorporating lighter components that support both strength and efficiency. As older aircraft are phased out, the transition to new models unfolds, creating a balance that supports the aspirations of aviation. The intricate network of design and engineering ensures that the fleet is continually evolving, adapting to the needs of the skies, while the gentle passage of time carries each generation forward into the future, ready to embrace the quiet promise of the open sky. Airplanes are predominantly made from aluminum alloys, materials carefully chosen for their unique properties. With a density of around 2.7 grams per cubic centimeter, aluminum strikes a delicate balance between strength and weight. This combination is essential for efficient flight. The lightweight nature of aluminum allows aircraft to soar through the sky with less energy, while its strength provides the structural integrity needed to withstand the forces of takeoff, landing, and various aerodynamic pressures. And aluminum alloys can be engineered to enhance their performance characteristics, taking advantage of different compositions that increase resistance to corrosion and fatigue. Over time, this careful selection aids in ensuring the longevity of each aircraft. The way these materials are bonded and assembled contributes significantly to the overall durability of the airplane, permitting it to navigate countless journeys through the atmosphere. Careful consideration of the molecular structure of these alloys allows engineers to anticipate how they will behave over time under variable conditions. This ongoing interaction between material science and aviation design continues to foster advancements that pave the way for newer configurations in airplane construction. There remains a steady evolution in the pursuit of materials that will guide the gentle glide of future generations through the endless expanse of the sky. Materials used in the construction of airplanes, including aluminum and various composite materials, are engineered to ensure long-term stability and reliability. These materials are designed with a fatigue life of around 20,000 flight cycles, which refers to the number of times an airplane can take off and land before any signs of wear begin to appear. This duration is important because it reflects the ability of these materials to sustain repeated stress while maintaining their structural integrity. The fatigue life itself is influenced by factors such as the microscopic structure of the materials and how they respond to pressure and temperature changes encountered during flight. The aluminum and composite forms allow for remarkable resilience against the gradual wear that naturally occurs with use. Over countless cycles, as the airplane ascends and descends, tiny changes occur within the materials, but they are designed to withstand this process for many years. Gradually, as these materials interact with the environment and experience the forces of flight, they begin a slow journey of change. Engineers continually study these effects to understand the thresholds at which materials may require maintenance or inspection. This careful monitoring ensures that the integrity of the airplane remains as stable as possible, allowing for a seamless experience in the skies. The ongoing relationship between the materials and their environment ensures that the journey through the atmosphere remains safe and serene, encouraging a sense of continued exploration. Navigation and avionics systems in airplanes are designed with the capacity for continuous updates, allowing them to remain functional and reliable over time. These systems integrate complex components that facilitate communication, flight control, and positioning in the air. They rely on a combination of sensors and software that work together to process information and guide the aircraft through varying environments. The heart of these systems lies in their adaptability. As technology evolves, new updates can be implemented, enhancing their capabilities without the need for complete replacement. This ensures that the systems can respond to changes in air traffic management, satellite navigation, and other emerging technologies. By incorporating ongoing advancements, the systems can maintain a high standard of safety. Each update is designed to improve response times and accuracy, allowing the aircraft to operate smoothly and efficiently. The infrastructure of the avionics remains robust, built to integrate new features and enhancements seamlessly. This continuity in technology fosters a sense of ongoing reliability. It allows the systems to remain connected with the latest advancements, promoting an atmosphere of trust as they continue to support remarkable journeys through the skies. The gentle hum of the electronics and the quiet precision of their function create an unseen balance, harmonizing the flight experience with the ever-evolving world of technology. The fuselage of an airplane is a crucial component, engineered to withstand numerous internal stresses while soaring through the sky. It serves as the primary structure, enveloping the passengers and cargo within. As the aircraft ascends and descends, the cabin experiences changes in pressure, creating forces that act upon the walls of the fuselage. These pressure variations demand that the materials used in construction retain their strength and integrity over time. The fuselage must also confront aerodynamic forces generated by airflow during flight. These forces can create bending and twisting moments, requiring careful consideration of material choices and structural design. Lightweight materials, often strong and resilient, are selected to ensure that the fuselage remains sturdy yet efficient. The long-term durability of these materials is paramount, as they must resist fatigue and prevent structural failure throughout the lifespan of the aircraft. Through meticulous engineering, the fuselage can adapt to these dynamic conditions, maintaining its shape and function. Layers of composite materials and metals work together to create a harmonious balance, dispersing the stresses evenly along its length. This careful crafting ensures that the aircraft remains reliable, allowing for countless journeys through the vast open skies, where each flight gently carries its promise of safety and security, enveloped within the strong embrace of the fuselage. At cruising altitudes, typically ranging from 30,000 to 40,000 feet, the air pressure is significantly lower than what is experienced at sea level. Here, the pressure drops to about 1/4 of the atmospheric pressure found at the ground, hovering between 25 to 30 kilopascals. Tonight, this alteration in pressure creates a need for a carefully designed cabin environment within the airplane. The fuselage must be constructed to contain a stable internal atmosphere, ensuring that passengers can breathe comfortably as the aircraft glides through the thin air above. Pressurized cabins provide a safe haven, maintaining an appropriate level of oxygen and comfort despite the harsh external conditions. The balance of pressure inside the cabin is delicately maintained, allowing for a natural and smooth flying experience. High-strength materials and well-engineered structures work together to create a resilient barrier against the external environment. As the aircraft ascends to its cruising altitude, the engines and systems work in harmony to adjust the cabin pressure, keeping it steady and suitable for those on board. The fabric of the fuselage, designed to withstand these stresses, becomes an integral part of the journey, ensuring a safe and serene atmosphere even amidst the vastness of the skies. The elaborate interplay between the pressures inside and outside the cabin unfolds slowly, providing travelers with a peaceful retreat as they traverse the clouds. Ground resonance is a phenomenon that can occur in older commercial aircraft, specifically when they are stationary on the tarmac. It arises from the vibrations of the landing gear, interacting with certain frequencies present in the structure of the aircraft. These vibrations are a result of the dynamic interplay between the aircraft's weight and the stiffness of its landing gear components. When the conditions align just so, the landing gear may begin to vibrate more intensely and resonate in a way that can influence the entire vehicle. If this vibration escalates without being addressed, it has the potential to lead to structural issues within the aircraft. The materials that compose the fuselage and landing gear are designed to withstand significant forces, yet the persistent resonance could challenge their integrity over time. Engineers account for these vibrations through careful design, ensuring that the aircraft can handle the stresses of landing and ground operations. Monitoring the frequency responses of landing gear in various conditions aids in mitigating the effects of ground resonance. This attention to detail helps maintain the strength and durability of the aircraft's structure. Each component works harmoniously to support overall safety, ensuring that even in moments of stillness, the aircraft remains resilient against vibrations that could otherwise challenge its stability. Such complexities unfold quietly, deep within the framework of the aircraft, creating a sense of reassurance as it rests on the ground, ready for its next journey into the skies. The landing gear of an aircraft is a marvel of engineering, designed with a focus on resilience and strength. It must withstand the forces that come with taking off and landing, absorbing repeated impacts that occur each time the aircraft touches the ground. Each component is crafted to endure not just the initial shock of landing, but the continual stresses from taxiing and movement along the runway. This robust structure includes shock-absorbing mechanisms that play a crucial role in this process, working to dissipate energy and minimize wear. Materials selected for the landing gear are often chosen for their ability to endure fatigue, allowing them to maintain integrity over a long service life. The design ensures that even after numerous landings, the landing gear remains reliable and stable. With each landing, the landing gear compresses slightly, absorbing energy that could otherwise affect the aircraft's overall structure. This careful engineering creates an environment where resilience is prioritized, allowing the aircraft to continue its journeys with confidence. As the airplane rests safely on the ground, the landing gear stands ready, a testament to thoughtful design, fully prepared to support the next adventure ahead. Softness fills the air as the world outside begins to quiet. Thoughts settle like feathers drifting gently to the ground, a hush enveloping everything. The steady rhythm of breathing slows, matching the calm stillness around. Each moment can feel expansive, as if time itself is pausing just to allow space for peace. Embracing this serene tranquility, the mind can unfurl like a delicate leaf, releasing the weight of the day. Eyes may flutter closed, inviting a gentle fog of rest. Comfort weaves itself through the fabric of stillness, cradling every thought and feeling. A soft embrace surrounds, letting go of tension. There is a safety in this silence, where worries can gently dissolve like morning mist with the rising sun. Gradually, the weight of the day loosens its hold, and the heart finds its natural rhythm. Breathe in deeply, exhale slowly. Each breath is a reminder of the calm that resides within. In this serene space, let thoughts drift like clouds, unburdened and free, finding their own path into restful slumber. As everything comes to rest, you are gently invited to surrender to the warmth of comfort. Rest, knowing that tranquility is here. It wraps around you softly, softly. Good night from Sleepy Science Facts.